Okay, so today's speaker is Cascioli, who will be telling us about the space of amenable subgroups of a countable group.
Thank you. Yeah, today I will speak about space amenable subgroups. So we introduce the space and amenable groups in general, and then see how this connects to property of groups. So it's in the crossroads of geometric theory, characterize, and dynamics, with this specificity. And that means definition through properties of unitary representations per group. See how they connect with the space amenable subgroups, and then see some examples where we can see explicitly how these two properties interact with each other. Let's go out for the talk. We will consider distinct countable groups. And there are some things that can also be generalized in the case of locally compact and countable, but there will be some essential differences that I will point out when we get to that. So G. Countable group. And we look at the space of subgroups. So it can be sub G. And this can be seen as a subspace of the space 0, 1 to G, just by identifying subgroups via the indicator functions. And this can be considered as a topological space with a product topology. This would be a compact space. And then this is a closed subspace that inherits a topology, which is called Shabauti topology. So we regard the space of subgroups of a countable group as a topological space, which could be this topology compact and metrizable. Maybe to have a feeling to what this topology actually means. This is actually kind of intuitive, the convergence of the space of subgroups, what you would expect from convergence of subgroups. So we are in the sequence of Hn converges to a limit at H. If and only if the following two things happen. One is that we want that every time we take an element in the limit subgroup, then this will eventually lie in the sequence Hn. And every time we take an element which is not in the limit subgroup, then it will eventually never lie in Hn. So precisely what you will think about convergence in a space of subgroups. And then we also have that our group G acts on this space, an action by homeomorphisms, which is just G action by conjugation. So the G acting on sub of G. An element acting on subgroup is just the G H G minus 1. So the orbit of this action will just be the conjugacy classes. So this is a G action on a compact space, and there are some information one can get by looking at this action on the space of subgroups, but in general this space can be really large and the dynamics can be really unpredictable. So one thing that one can do is, instead of looking at this general space of subgroups, to restate to a subspace of this, which is the one given by amenable subgroups, where we will see that the dynamics can be described much better and gives explicit information on the group that we are considering. So I will define what amenable groups are in these examples and then see how we can look then at this subspace inside sub of G. So amenability is a property which is central in geometric group theory, and it admits a ton of different characterizations. So my favorite one is my favorite just because the first one that I studied, so that's just the one that I say into my mind, and it's the one through the existence of a G invariant mean on the space of functions on G. And all these different characterizations that amenability has kind of revolve around a common theme of being almost invariant with respect to something. So say somehow amenable groups are supposed to behave well, they are flexible enough so that they admit a way of averaging over themselves, which is invariant with respect to the action on the group on itself. So formally this means that group G is amenable. G invariant mean. That is an Arminian map M from L infinity of G, so that's space of bounded function for G to R. That satisfies the following conditions. One, it's normalized, so M of 1, where it's just constant function at 1, to be 1. Then we have that it's positive, so M of F is greater than equal to 0 if the function F is pointwise greater than 0. And this is what it means to be a mean. Then we add this G invariant condition, so M of G acting on F is the same as M of F for every element of the group and for every bounded function. Where the action that we have of G on this base of subgroup, on this base of functions, is just action by left translation, meaning that G acting on F computed an element H is just translating the argument this element G, so this will be F of G minus 1 H. So then one can give this definition to the existence of this mean. One, for example, can also define amenability by saying that the group is amenable if and only if, whenever you look at an action by homeomorphism of the group on a compact adjustable space, this action will admit an invariant probability measure. So again, this notion of something being invariant. There is also an intrinsic characterization, just by looking at the subset of the group through the existence of corner sets, which is almost invariant, which are basically almost invariant subsets again with respect to the action on itself. So all of these definitions around this common theme of invariance. And by using this definition, one can already see kind of directly this is a simplicity test. That amenability holds for some nice classes of groups. For example, the first thing that one can do is to show that the finite groups are amenable. So in this case, we can directly write what is the mean of a function. So this is just the average that you would expect. It's just the weighted average of the average of the value of the function on the elements of G. So in this case, we can write directly what is this G invariant function. And then one can show that abelian groups are amenable. And in this case, we do not have an explicit way of writing a mean, but the existence of a G invariant mean comes down to using a fixed point theorem on the space of means on the group. So with the real set topology, and then you look at the action G on the space of mean, and a fixed point will precisely be a G invariant mean. So one has to use a function analytic argument. And then amenability also has some very nice stability properties. So for example, it's a property which is closed under direct limits. It's a property which is closed under group extensions. So in particular, this tells us two important things. That if we look at subgroups of an amenable group, the subgroups will also have to be amenable. So whenever we have something non-amenable inside, we know that the group itself will be non-amenable. And then this implies also that we can extend from medium. We can also say that all solvable groups are amenable. So up to now it seems that like everything is amenable. Well, of course, this is not an infinite if because you can find finite groups which are not solvable. So, but then the most important examples of non-amenable groups is given by non-abelian free groups. Are not amenable. So here I will write Fm mean the free group of rank M. So just the group of reduced words on an alphabet of M letters, where the only interaction between the elements of the groups are just given by the ones that define the group structure itself, and no other interaction exists among the elements of the group. So as I mentioned before, if you contain something which is a subgroup which is not amenable, then you know that the group will not be amenable. And it was actually an open question for quite some time to understand whether containing a non-abelian free group is actually a characterization of being non-amenable, which was actually then proved to not be true through the existence of some groups which are non-amenable but do not contain F2. And one of these examples given by rivers and groups that I will then mention later in the talk. Okay, so maybe before going, I will give explain that example and explain why these groups cannot admit invariant means. So we cannot by F2 just the free group of rank 2 and show the case of F2. So if M is an invariant mean of F2, write F2 as generated by just two letters A and B. Then we can consider a special subset of elements in F2 that we denote by capital A, which is given by all reduced words in F2 that starts with an integral power of this first generator A. And then we have that if you take A union A minus 1 A, this will give the whole group F2. So then we find a contradiction by looking at how this invariant mean would behave on characteristic functions of certain subset of the free group F2. So if we look at M computed on the characteristic function of the group, then of course this will be M of 1, which is 1 because of the properties of being a mean. But then this will be less or equal than M of the characteristic function of A plus M of the characteristic function of A minus 1A. But then this will have the same value because we're looking at a mean. So it's just twice M of the characteristic function of A. So we have that when we look at a specific subset of elements of the free group, this will have through this mean at least 1 over 2. But then we can consider other subset of F2. We take A, B, A, and B squared A. And we notice that these are all disjoint. which then implies that, again, if you look at the characteristic function of the whole group, this will be greater or equal than m of the sum of the characteristic function of all these three subsets. So A, B acting on A, M squared A. But then again, these are the same. So you get that this is 3 times which over 2, which gives a contradiction. So this is a very direct way of seeing that just by playing around with some subset of the free group, somehow we have too much freedom to actually admit a mean that is invariant, because you will get a contradiction by looking at the value of this mean on certain subsets. So free groups are really like the typical examples of non-abelian groups, and kind of often all the groups that also show behavior which is far from being amenable are all groups that somehow resemble free groups in certain ways. So now that we have this the definition of amenability, we can then restrict to the space of amenable subgroups of the group G. And we denote this by sub of G. And this will be closed and G invariant. So in particular, this will be again a compact space on which the group acts by conjugation. So the fact that this is G invariant, it's immediately just comes from the fact that the orbits of just the conjugating classes, and subgroups that are conjugate to each other are isomorphic, so amenability is preserved. And the fact that it's closed in the case of discrete countable groups is just shown by using basically the definition of the topology. But it's interesting to see that this is an open question if we move from discrete groups to locally compact groups. So this is open if open question if G is a locally compact. So here we see that there's a clear difference if you look at discrete and locally compact groups. It has been proved that this is always a Borel subset of the space of subgroups, but it's still not known whether it's closed. It's known that it's closed if you restrict to certain classes of locally compact groups. For example, if you look at connected locally compact groups, but in general, it's still not known. Okay, so we have this space when you have the subgroups, and we said we want to see which information we can get then from seeing G acting on this space here. And what I'm interested about, especially then with the research that I'm doing, is to see the connection between this action and the property of sister simplicity. So as I mentioned at the beginning, sister simplicity is a property of groups that is defined in operator algebraic terms. But somehow similar to amenability, then when it started being explored more, people found equivalent characterizations that are also purely group theoretical, more in topological dynamical settings. So I will give the definition.
Can you write a bit larger?
Sure. Yeah.
So the recording.
So to define what sister simplicity is, we first need to define what the reduced sister algebra of a group is. And we start by considering the space, the inverse space L2 of G of square sum over functions. Then we know that G acts naturally on the space of functions, again by left translation. And this allows us to get a representation of the group. So we have denoted by lambda, G, the bounded operators of the hyperspace. So to each element of the group, we associate an operator lambda G, which encodes this action by left translation. So lambda G F acting on H is again just F G minus 1 H. And this lambda is called left regular representation of the group. Then we want to define a sister algebra that we can construct starting from all these left translation operators. So it's not really relevant for us for the sister algebra, but we just need to know that it's an algebra of operators, which is closed then in the space of bounded operators on the hyperspace. And so the way that we do it is that first we look at finite linear combinations of such operators, and then we just close under the operators model. So formally, we define the reduced group sister algebra in the following way. Use algebra C star RPG. So as I said, we take finite linear combinations of these left translation operators, which means taking the image through this left regular representation of the grouping of G. And then we close this under the operator topology. This will be something inside the bounded operators in superspace. And then we say that the group is sister simple if this algebra of operators is simple in the operator algebraic sense, meaning that it has no non-trivial closed two-sided ideas. So maybe before looking at some examples, let's understand 1 second what is the point of giving this definition. So if we're working with finite groups and we're looking at the representation theory for finite group, basically all the information will be encoded in the group ring that we can construct looking at this left translation. So in this case, this object already has all the information as a representation. We can also then write it as the direct sum of all the reduced representation with the multiplicity given by their dimension. So in that case, this will be a finite dimensional space. So it's complete in every sense. There isn't much to say from a function analysis point of view. But then when we move into the context of infinite groups, if you look at this will not be closed inside the space of bounded operators. So the natural thing is to take the closure, and then this will be the object that actually behaves in the way that we want for in the case of the infinite group. So that this is the point of giving this definition in this case of infinite groups. And this property was introduced in 1975 by Powers, and he proved at first that non-abelian free groups are sister simple. F2 is sister simple. And then he was proving that other groups that satisfy a certain operator algebraic property called Power's property will also be sister simple, but at the time, the only tool that was known to investigate this notion was to really understand the structure of the reduced group sister algebra and analyze the cases in which this sister algebra was sister simple. So it was really a property that was approached only from an operator algebraic point of view. Then at some point around like the 80s, there was a shift towards more like geometric group theory approach to this property. So it was proven that several groups that arise naturally in geometric group theory are sister simple. For example, if you look at non-elementary hyperbolic groups, they will very often be sister simple. And then even later, around 2010, there was another shift to a more dynamical approach with a breakthrough result where it was proven that a group is sister simple if and only if it admits a topological G boundary, where the group acts topologically free on such boundary. So a characterization which seems a priori really far from an operator algebraic setting that we are seeing now. And from this topological shift, it was also possible to then give a very intrinsic group-theoretic characterization of sister simplicity that we will see connects directly to the space of amenable subgroups. So first, it's worth saying that if we look at amenable groups, non-trivial amenable groups, this will not be sister simple. So we see that three groups that are the prototype of non-amenable groups also are the prototype of sister simple groups, and amenable groups are completely on the other side, also for this operator algebraic property. And it's worth saying also here that one can give the similar definition, an appropriate definition of reduced group sister algebra also for locally compact groups. But then it turns out that the sister algebra that you get will be unitary if and only if the group that you start with is discrete. And it's not very nice to work with non-unital things, so you don't have the identity. So there has been some work on the case of locally compact groups, but most of the things are done for discrete groups for this reason. Okay, so we see here that amenability gives clear obstruction to sister simplicity, but it turns out that actually not only being amenable, but already having a rich amenable structure of space of subgroups actually prevents a group from being sister simple. So the first thing one can do is to define the amenable radical of a group G, denoted RA of G. And this is the largest amenable normal subgroup of G. And one can prove that this always exists by using John's lemma and the stability properties of amenability. And it turns out that if you are sister simple, we can also see it more explicitly later, that if the group is sister simple, then we will have that this amenable radical has to be trivial, meaning that you cannot have non-trivial amenable normal subgroups in the group G. So not only being amenable means that you're not sister simple, but already having normal amenable subgroups will obstruct sister simplicity. And again, here it was open for quite some time to understand whether this was a characterization, because it was quite difficult to find counterexamples in the other direction. So this was done by Le Boudec, a very important paper on the subject. But it actually turns out that in many classes of groups, the if and only if actually holds. So this example, it's actually quite complicated to construct. So the if and only if holds in many cases. For example, if we look at discrete linear groups, and also if we look at the class of asymmetric hyperbolic groups, which is also a class of groups very important in geometric group theory, which includes non-elementary hyperbolic groups. and it includes also some mapping class groups, automorphism groups, some three-manifold groups, and a lot of objects that come from geometry. And also, for example, this holds if you have countably many amenable subgroups and in other situations. But it was still an interesting question to understand then to what extent we can get an if-not if here, so in which way we can actually characterize this property by looking at the structure of amenable subgroups here. So the next step will be actually seeing a characterization of the simplicity with this approach. As I mentioned before, intrinsic group characterization was given after the shift to a dynamical approach. So the theorem that I will mention now was proven in 2015 by Kennedy. So Kennedy proved that a group is still countable group G is sister simple if and only if we look at the conjugated class of every amenable subgroup G, this accumulates an identity in this space, this compact space of amenable subgroups. So the conjugacy classes are again just the orbits of the action that we have. So we have this topology on this space of amenable subgroups. And basically here we're saying that G is simple if and only if the dynamics on the space really collapses down to the trivial subgroup. So as I mentioned at the beginning, the general space of subgroups can be really large and things can be really unpredictable. But if we restrict to the amenable subgroups, then really the collapsing to the trivial dynamics quantifies if the group will be sister simple or not. So there is really this if and only if characterization in this case. And if one wants to look at this theorem in a purely group theoretic language, so without using the actual topology on the space, this would be the same as saying that the group G has no amenable subgroups that satisfy a property for which they are called concurrent. Now this property also has other names, like some people call it residually normal. There are some other ways of looking at this property, but I will use this notation here, which means, so what is an amenable recurrent subgroup? Will be an amenable subgroup H of G, such that we can find a finite subset F of the group minus the identity that intersects non-trivially all the conjugates of H. So F intersect G, H, G minus 1 is non-trivial for every element of the group. So being amenable recurrent subgroup means intuitively that this subgroup will be very visible in the space of subgroups of G, so that we can just see all the conjugates by looking at the finite region of the group. So basically here we're saying that the group is sister simple if and only if, whenever we take an amenable subgroup of G, we can conjugate it away from every finite region of the group. So somehow we'll escape every finite part of the group that we're looking. So this is the same. I mean, one can see it quite easily that this is if and only if it's literally just explaining in purely group theoretic terms what it means for the conjugating class to accumulate that identity. And by having this theorem, we can see some immediate corollaries. So one is that we see directly that if GCs are simple, this implies that the amenable radical has to be trivial, as I mentioned before. Because of course, if you have an amenable subgroup which is normal, then all these conjugates will be just the subgroup itself. So we will not accumulate an identity, we will stay at the subgroup itself. And then we also have that if GCs are simple, then the group will be ICC, so infinite conjugacy class, meaning that the conjugacy class of every non-trivial element of the group is infinite. And this can be seen again because if that was not the case, and you have an element X with finite conjugacy class, then the cyclic subgroup generated by this element would be an amenable recurrent subgroup in G. Okay, now that we have this theorem, I would like to look at some examples where we can actually see more clearly how this space of amenable subgroups behave. And the first example that I will give is again looking at what happens for free groups and show that by using this characterization, it really takes nothing to prove that the SSs are simple by showing that the dynamics on a space of subgroups collapses very easily to all the conjugacy classes accumulating of the identity. The dynamics on the space of amenable subgroups of F2 on two letters. So first of all, what is the space of amenable subgroups? So of course we will have the trivial. But then here we just need to use important theorem in group theory, the Münster theorem, that says that if we look at a finitely generated free group, then every subgroup of it will be free again. And then we know again that for the stability properties of amenability, if you contain non-abelian free subgroup, you will not be amenable, which means that in this case, the only things inside here will be the cyclic subgroups generated by non-trivial elements of the group. So in order to prove that F choices are simple, we just need to prove that all these cyclic subgroups are never recurrent. So it's never recurrent. We do it in the following way. So first of all, we write the group F2 again generated by A and B, where we can choose the generators in such a way that our element X that we're looking at is not a power of the first generator A. Then, if we assume by contradiction that this is a recurrent amenable subgroup, so if we can find an F inside the group one's identity, which is finite, that intersects all the conjugates, by example generated by Gx G minus 1. Then what we can do to get a contradiction is that we choose the element G that we are conjugating with as higher and higher powers of this generator A. So A to the n with n, the closed larger tree. So what we get here, so since you will not cancel completely here, we're taking x, which is not the power of A. Inside these conjugates, we will get words that grow larger and larger because we're conjugating by elements that grow larger and larger. So what we get is that we can make the minimum reduced word length in these groups G, X, G at G minus 1 minus identity, arbitrarily large. Again, by conjugating by this longer and longer powers of the generator A. And this is a contradiction because F is finite. So in F, we must have a maximum reduced word length. So this means that there is no way that we can actually see all these conjugates just in a finite region of the group where we would have that the words cannot grow arbitrarily large out of the group. So this implies then that the group F2 does not have amenable recurrent subgroups, so F2 will be sister simple. So as you can see, this is really just like group theory on the space of subgroups and really nothing else that relates to the actual reduced group system algebra or other things of the free group. And then to finish, let's look at another example that I mentioned already at the beginning, which is given by free Münster groups. So these groups play a fundamental role historically in group theory because of the following question posed by Burnside back in 1902. Asked whether a finitely generated group with bounded exponent it has to be necessarily finite or if it can be infinite. Where this just means that we can find an n such that every nth power of elements in the group is the identity. So we have the finite generated in this question because otherwise one would find these trivial examples like just taking infinite products over z of z over to z, so it's not really interesting. But yeah, this question has an extremely easy formulation, so it can be understood by someone who has really taken like 2 weeks of group theory. But it turns out that the answer was really, really difficult to give and was actually given more than 60 years after when the question was posed. And so the answer would be negative and makes sense then to look at these groups. So free set groups that we give a negative answer to these questions, which are defined in the following way. So this is the notation for the free group of rank m and exponent n, which is defined as the quotient of the free group of on m generators over the normal sum generated by all n powers of words in the free group. So why does it make sense to look at these specific classes of groups when you want to answer this question? Well, the point is that these reversal groups are the largest M generator groups of exponent M, meaning that every other group will be a homomorphic image of such groups. So if we want to prove that these are infinite, then we will actually answer more generally the question. And so, as I mentioned, this was proven by Adyan and Novikov. 1968, that these groups are infinite if we take at least two generators, and if we take exponent odd large enough. So the first group was 4,381, and was lower a bit. So this is a negative answer to this percent problem. And this proof was really, this is really a breakthrough resulting group theory. However, it's a 300 pages proof, which is basically impossible to read and to say. It's an induction hypothesis where you have 178 induction hypotheses, so kind of difficult to keep track of everything. So there was then a recent improvement by Matkskaya. Sometime 2023, who proved that these groups are infinite if we take odd and is 557, which is at the moment the best lower bound that we have. And also apart from the lower bound, this is still an induction hypothesis, but we have 13 hypotheses instead of 178, so it's a very different thing to read compared to the original proof. And it's interesting to know that, okay, it's known that these groups are finite when we have exponent 2, 3, and 4, and when we have exponent 6, but it's still open to know whether they are finite for exponent 5, and then for exponent greater than 7. So there is really a gap of more than 500 where we have no idea if these groups are finite or infinite. So there's still a lot to know about these groups, which is, I would say it's a bit surprising when you see the actual representation. It seems very clean. You're literally just taking a free group and you're imposing this relation. So it's very easy to write. But as the question is to formulate, then the groups are actually very difficult to understand. And the point is that when you look at very high exponents, somehow it's nearly as if you don't even see the torsion in the group. So if you go to very large exponents, then this will kind of behave as very similar to free groups. But there's a really a large, from 7 to 257, when you really don't know what's happening there.
What if the exponents of algebra 2?
So if the exponents of algebra 2, there are also results that were proven later. So it was also proven for even exponents. So at the beginning, it was proven that you can say that they're infinite if it's true to the an insane amount. So it was more of an existential proof. Then this was lowered a bit, but it's still very far from something like 500. So in the case of even exponential situation is much more complicated, and the point is actually because the space also the space of subgroups becomes much more complicated. You have all these evolutions that really mess up structure of the group. And many things that you can say for these groups about exponent are really heavily rely on the fact that you have no evolutions. So it's really a different approach in the two cases.
Are these two numbers spectral? Is there something behind these numbers, or they are just gathered by case discussion?
So in the case of this 157, it's not that the number itself has a special meaning, I would say, but it does come from the fact that this proof is all given by basically combinatorial small cancellation. So you basically control how much words can overlap inside the three-percent group, and you fix a constant for which you know that if words overlap, then they have to be the same word, kind of. and then this number will be just a function of that constant. So at the moment, this is the best known where this constant that they use is 15, but they do hope that maybe there's something that can be improved. So it comes from the actual like structure of the proof. For this, for us, 4007, because the proof is really a little. But this was also like then brought down to like 600 something. So they also improved the regional work. So what can we say to finish about then the amenable subgroups of Münster groups and how it relates to the simplicity? So first of all, it's worth to know, this was also proven by Adrian, that again, if we take m at least 2 and all exponents of large enough, then these groups will be non-amenable. But one can see just by the definition that these groups do not contain free subgroups. So this gives example to the fact that that conjecture of amenability being equivalent to not containing free subgroups actually not true. So this is also interesting from the point of view. And it was proven by Olshansky that these groups are sister simple. But this was before we actually had this group characterization. So then the proof here is not really that easy. But if we actually look at the structure of the amenable subgroups, then we can directly apply Kennedy's theorem and show that these groups will be sister simple. So we can just look at the space of amenable subgroups. So here again, everything is done for odd exponent large enough. And one can prove the following two things. So it's useful to divide, in this case, the amenable subgroups in abelian and non-abelian. So if we look at the non-abelian, one can show that these contain a copy of the Hilbert set groups V2n, so for the same exponent, which then implies by this result by Adrian that all the non-abelian subgroups will be non-amenable. So we do not have non-amenable things, non-abelian things inside the space of subgroups. So then you just have to look at the abelian ones. And one, in this case, can show that these abelian subgroups are just cyclic subgroups of finite order. Which then easy to see that this implies that they cannot be recurrent. Because if you add that these finite cyclic subgroups are recurrent, then you would have finite conjugacy class for the definition of the recurrent, but then you would have that G on the centralizer, which is amenable, which is abelian. This would have to be finite because it's number of conjugacy classes, but this is finite, and that G would have to be finite, but this is not the case for large exponent, odd large exponent. So this implies that just by looking at this subgroup structure, one can see again that this group is not sister simple, so you can that is sister simple, sorry. So you can recover this known result that was known through more operator algebraic methods by looking directly at the dynamics on the space of subgroups. Which I think also it's interesting to see how actually things behave in a more explicit way, and to see really how these dynamics here can show that things can collapse very easily and prove sister simplicity in this way. Thank you.
Sana. Any questions? Yeah, I guess what class of groups are you looking at next to show C-star simplicity or not C-star simplicity using these methods?
So what we're looking at is kind of looking at concept quotients in the sense that we take groups and we take again this the quotient over n powers. So for example, if you look at things of this form, if you look at three products, and then you quotient over n powers, so in this case you take n powers of words which are not say contained in the union of say they're not conjugate to things in G or H. Your H. Then you can prove that this will be sister simple using a very similar approach because you will have a very similar behavior of the space of subgroups. And then the hope is that we want to extend this also to maybe portions of HN extensions. So all things that kind of like you start with three groups, go to three products, then you go to HN extensions. But it's not that easy because the general approach really relies on the definition of a canonical form for cosets in the Fibonacci set group. So for example, if then you go into HN extensions, then you already have a normal form that it's not unique but depends on some choices. So if you want to put together somehow a unique way of looking at elements, is not that immediate to see if you can do everything. But that's kind of the general approach, is to describe in a unique way elements of these groups, and then everything is like unilateral cancellation and how words interact with each other.
And you mentioned that you can do similar things for, well, the definition sort of makes sense for not discrete groups.
Yes, but I know that there has been a few papers on the simplicity of locally compact groups, but again, it's something which has not been really explored that much because of what I mentioned on the fact that you do not have a unitary sister algebra. So I don't really, it's an interesting topic and there are many people working on it, but I don't really know if one can extend also some of the results. But I mean, in this context, also given to the fact that you don't know what happens in the space of amenable subgroups, so then it's really like open to understand if there are connections, but it's still interesting to see if like separately we can answer these two problems in the case of locally compact groups.
Maybe a stupid question. Have you ever tried other independent groups, say the Artin group or the independent of subgroups?
No, but I don't really know. I think about it, what is known for the sensitivity of those groups. I guess some of them will for sure fall under some of the classes for which sensitivity has been proven, because it has been proven for autoproof constructions. There is a very nice paper by Pierre de la Harpe where they look at sensitivity of like autonomous group constructions. So I'm sure something might fall there. But for now, I'm looking more at like figure side groups. Thanks. Yeah.